Hello friends, this is lecture number 19, complex analysis. Today we are going to discuss about Lorentz theorem. Before that, I would like to suggest that first, what's the previous lectures on Cauchy's integral formula, and Taylor's theorem. Okay, then it will be easier to understand this topic. Okay, and I have given all the previous lectures, link of the previous lectures in the description box, so you may go through if you want. And before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, hit the bell icon so that you get notified when new video will be uploaded, and support me to create new contents for you, support me to grow my channel. Okay, so now let's start. So Lorentz theorem. So what is the statement of this theorem? Let me write the statement first. So now you see Lorentz theorem. If a function f of z is analytic on C1 and C2, and the annular region bounded by concentric circles C1 and C2 of radii R1 and R2 respectively, okay, where R2 is greater than R1, and with the center small a, then for all z in R, f of z can be written in this way. Let me write that series first. Okay, let me write that series. So this is the series that we're going to obtain. Okay, that the function f of z can be expanded. So, or you can write this way as well as in this way. You can write using summation. And let me write the where the values of an and bn are this. These are the values of an and bn also. Bn is this. This is bn. Right. So this is the value of bn. Now you see, when we use this theorem, now this theorem is required to expand a function f of z about a point where fz is not analytic. Okay, so in Taylor series, what we when we used to expand a function using Taylor series, so when we have to expand about a function f of z about a point where this is analytic. In that case, we used to use the Taylor's theorem. But suppose we have a point, right? So here we have taken two circles here, C1 and C2. Here you can see C1 and C2 of radii R1 and R2 respectively. So I have taken the radii R2 and this is R1. So C1 is suppose directed in this way. This is the direction, and this is the direction of C2. Here radius of C2 is R2, which is less than radius of C1, that is R1, and the region bounded by these two circles. Okay, in this region only f of z is analytic, right? So we have considered, suppose we have to expand this about a point, expand this function about a point, about a region which is about a point which is not in this region where this function is analytic. If a point which is suppose inside this both the circles, so here this function is not analytic. If we need to expand it about this point, then we're going to use this theorem, and then this series found from this is something like this. Okay, where value of an and bn are given. So n is equal to 0, 1, 2, dot dot dot, so on, right? So hope you have understood this. So first pause the video and note this theorem, and now let me explain how to prove this. So in order to prove this, you must know the cauchy integral formula. So that's why I request you to watch the video made on cauchy integral formula. So let me clean this. Now let me explain this, how to prove this one. So here you see, first let me tell you about the cauchy integral formula. Just let me give you a brief explanation as we need it. So here we suppose have a closed curve C. This is a closed curve C. Suppose this is a closed curve C, right? This is a closed curve C, and we have this function f of z, which is analytic within and on this curve, within this curve and on this curve. Okay, this is analytic, and its center is suppose A, right? Then f of A is given by 1 by 2 pi I along C f of z minus A. So we are going to apply this, right? Now you see, as in this theorem we have taken in Lorentz theorem, that we have taken two circles, concentric circles, C1 and C2, right? C1 and C2. So direction of C1 is this, and direction of C2 is this, and this region, only this region are the function f of z is analytic, right? And here is the center A, and now you see, in this case, in order to apply this cauchy integral formula, here we had f of A. Now we are to expand f of z. So f of z, so here in this case, in this formula we are going to replace this A by z, and this z should be replaced by another variable. Suppose let us take w, and which is in the region of where this function is analytic. This w may be on this circle, between these two circles, or on this circle C1 as well. Okay, now in that case, if you replace this A, then by z, here if we apply z, then here it is, suppose z is replaced by w minus a, z minus a is replaced by w minus a, then this f of z should be f of w, and there should have been a dz. So this dz is replaced by now dw, okay, dw, okay, and this is along suppose C1. So as we have two circles, and if we use a cut here, okay, to connect these regions, so this is suppose AB, and this is BA, AB and BA. Then now if we apply that theorem, this cauchy integral theorem, then we can write this result in this way. So we have to integrate along both the circles and along AB and BA as well. Okay, now we have to integrate along C1, C2, along AB and along BA as well. I'm gonna write all these things properly. Okay, first let me explain. Okay, I'm gonna give you proper notes while I'm gonna explain. I'm gonna write it properly, but let me explain the basics first. Okay, so then this can be written in this way, that this is along C1, then plus again 1 by 2 pi I along AB, this is FW by W minus Z. You don't have to note these things now what I am writing. Okay, you're gonna get I'm gonna write it again properly, and just let me explain some few things. Let me make few things clear how to proceed. Okay, so here dw, then again we have to integrate it along C2. So if you see the direction of c1 and c2, they are opposite, so we're gonna use the minus sign, 1 by 2 pi I, then again f of w along c2 here, w minus z dw. Then again here we have AB. Now we are going to integrate along opposite direction. That's going to be again negative, right? That means here you see, if you integrate along BA, if you make the BA AB, then this positive sign going to be negative. So just let me write first. Let me apply the formula along BA. Okay, so it should be plus BA. Sorry, I forgot to put the 1 by 2 pi I BA f of w minus a. Instead of a we have z now, f of z dw, right? So if you make this BA AB, okay, instead of BA if you write AB, then this minus this plus sign, this plus sign gonna be minus. Okay, this plus sign gonna be minus, right? And that's what we have done here, and these two gonna be cancels, right? So now let me write the things properly. Okay, what are the things to be considered and how to proceed. Okay, so now let me explain all these things. Okay, so here is the proof. So these are the two circles, C1 and C2, with radii R1 and R2 respectively. And here you see, by introducing a cut, cross cut AB, this multi-connected region C1 and C2 bounding R, converted to simple connected region. Okay, so here we're going to use cuts. Okay. Now if f of z is analytic in this region, then by Cauchy's integral formula, as I have already explained, then what we can write this f of z is equal to, so let me write these things what we have done. Let me write let me make this cut here. This this is the direction. This is AB, then in this direction it's gonna be BA. This is AB, BA, right? So hope you have understood this. So now let me continue. So how to obtain this result, I have already explained before writing these things. Okay, how to apply this Cauchy's integral formula. Okay, so that is what we have got. Now this can be this gonna imply this, right? So now you see, we're gonna make the BA as AB. We're gonna write BA AB. Instead of BA, we're gonna write AB. Then this positive become negative, right? So that's what we have got. Now these two terms cancel, right? So what we have got. So this is the final expression that we have got. So now let us take this one as equation number 1. Right, let us take this one as equation number 1. Now let us find, we have two integrals, first and second. So let us deal with the first integral, this one, first one. Okay, now let me go to the next slide. Okay, so here you see f of z 2 pi I c1. Let me write the equation number 1 again here. So let me draw it again. Okay, so here you see so here for the first integral we're gonna consider that that we have this w on c1. This w is on c1. Okay, and we're gonna proceed as the way that we did in Taylor's expression. So right, we're gonna proceed in the same way as we have done in Taylor's theorem, right? So what we should do now, what we're gonna get here, you see, first we're gonna expand this 1 by w minus z. Here it can be written this way, here minus a plus a. If you cancel minus a plus a, then you're gonna get this again, right? That's what we're gonna have. So now you see this is gonna be equal to this. So what we have done here, we have taken w minus a common. Okay, so then from here we have taken the minus sign common. That's why it's become z minus a, right? So hope these things are clear to you, right? So now what we're gonna get here, if you expand, you're gonna get this, right? So here you see, let me tell you, so how to expand it. So here I have used this 1 minus x whole to the power n. That's gonna be equal to, that is equal to 1 plus x square plus x cube plus dot 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 dot, so on. We have taken this is 1, this is x, right? And using this we have expanded this term, right? And after expansion of this term we have multiplied the result by this term, so we have got this result, right? So then what gonna be the first integral, what gonna be the value of the first integral? Here we're gonna take right, since w is on c1, right? So if we use this result, use this expansion here, then we're gonna get, let us use this result here, then we're gonna get this result here. You can see you're gonna get it, right? Now let me take a new slide and let me go to the new slide and let me copy this result. Okay, first let me take a copy this result and let me go to the new slide. So let me write the last result that we have got here. What we have got, so this is the last result we have got in the previous slide. So now here what we can do, so we can, this can be written this way, just wait. So I have written 2 positive sign, yeah, it should be something like this. Okay, so this is what we're gonna have, right? This, let me take this as equation number 2. Sorry, this is along c1, right? Let us take this as equation number 2. So here you see this an, we can write an is equal to integration this, right? I have already mentioned earlier that value of an is equal to this, and where n is equal to 0, 1, 2, 3 and so on. So here you see, if you put here n is equal to 0, if you put n is equal to 0 here, then you're gonna get this term is equal to a naught. And similarly, if you put n is equal to 1 here, then you're gonna get this part gonna be equal to a1, right? Similarly, if you put 2, then you're gonna get this part is equal to a2, right? And so on. That's how we have got this series, right? So let it be equation number 2. So we have taken this as equation number 2. So now here you see, this is the first integral. So what is the second integral? What about the second integral? in the second integral, let me write the second integral. So what was that? So here you can see this is the second integral here in equation number 1. This is the second integral. Now let us evaluate this. In order to evaluate the second integral, we're going to consider that this w is on c2. This w is on c2, right? In order to evaluate this second integral, we're going to consider w lies on c2, and first we're going to expand again this 1 by w minus z part in this way. Okay, so let's do that. Go to the next slide. Here you see, so here we have considered w lies on c2, right? So again we have written 1 by w minus z in this way, 1 by w minus a plus a minus z. Okay, then what we're gonna get, if we expand, then again we're gonna get this result. So here w lies on c2, so w minus a must be less than z minus a, right? So this can be written in this way. So here you see what we have done here. We have taken this one common with this minus sign, right? And so we have got this, which can be written in this way. And again we have used this 1 minus x whole to the power n. Its expansion is 1 plus x square plus x to the power 3 plus dot 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 so on. That's what we have used here, right? So now let me go to the next slide. Here you see, before that let me tell you what we're going to do. Now we're going to use this value here in the second integral. You can see, let me go to the previous slide here. In this case you can see this is the second integral along c2. This is c2, so there is a minus sign, and this 1 by wz in this this time it's gonna be replaced by this result, right? So then what we're gonna get, let me go to the new slide. So let me rewrite the last result that we have obtained. This is the last result we have obtained. Okay, so if we use this result in the second integral, here you can do actually two things. Either you can substitute this value in the second integral, here, or you can multiply both sides of this result, or both this both sides of this equation by this term minus fw by 2 pi and 2 pi I. Then what we're gonna get here. So the result's gonna be something like this. This is what we're gonna have after the multiplication, right? Now let us integrate this result. Okay, so now here you see this is the result we have obtained. Now let us integrate this with respect to w. So then what we're gonna have, we're gonna have this result. So this is the result that we're gonna get. So let me write it here. Just switch. So let me put the integration here. So integrating this, what we have got, we're gonna get this. Okay, so now let me go to the new slide. Let me copy this result and let me go to the new slide. Here what we have got here, this is the result we have got. Let me write it again. So integrating this result, we have got this, right? So now we can take this z minus a term common outside the integral, because we are integrating with respect to w only. W is the variable, others remaining terms should be considered as constant. So that is why we can write this way. The above result can be written this way. Now here you see, this is the just one more thing, we can replace these things. Here you see this one by b1, this one by b2. Let me tell you how. First let me write the result here. This is equation number 3. This is nothing but the second integral. So what is b1, b2 and b3? So we have already mentioned earlier that bn is equal to nothing but 1 by 2 pi I integration along along c2 f of w dw by w minus a whole to the power minus n plus 1. Okay, so bn, value of bn. So if I have written here c1 earlier, then make it c2. Okay, so bn, it should be integrated along c2. Okay, so make it correct, where n is equal to 0, 1, 2 and 3 dot dot dot. If you put n is equal to 0 here, then you're gonna get this is equal to b1, and if you put n is equal to 1 here, if you put n is equal to 1 here, then you're gonna get this is equal to b2, and this one you're gonna get b3, and so on. That's what we have got. So now let me write the equation number 1, 2 and 3 in the next slide. Okay, let me go to the next slide. So here you see this was the equation number 1, right? So let me write the equation number 1, and let me write the value of first integral, that is this is equation number 2. This is the value of first integral, right? So similarly, let me write the second integral as well of the equation number 1. This is the value of second integral of equation number 1, right? So equation 2 and 3. Now let me use this equation 2 and 3 in equation number 1. So here you see this is the value of this first integral, and this is nothing but the second integral. So here we have got the value of this. Now you can assume this one as plus this one, right? And let us replace this by this result, and what you're gonna get using 2 and 3. So using 2 and 3 in 1, we can write f of z is equal to a0 plus a1. So there should be only one positive sign, so I made 2. Okay, z minus a plus a2 into z minus a square plus dot 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 so on. Then we're gonna get plus b1 by z minus a, b1 by z minus a, then plus b2 by z minus a whole square, then plus dot 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 so on. That's how we're gonna get, right? So, and this can be written in this form as well using summation. Using summation, we can write f of z is equal to, so you can write z minus summation a n z minus a whole to the power n, right? And where n is equal to 0 to infinity, right? We can write that way as well. And we have we can express this second part, b1 b2 terms containing b1 b2 in this way, plus summation n is equal to 0 to infinity bn, let me write just bn by z minus a whole to the power n. We can write that way as well, right? So hope you have understood. So the final result we have got is this f of z. That is what we have got. Let me write it properly. Let me go to the new slide. This is the result we have got, final result, right? This is the Lorentz expression, and which can be written in this way using summation from n is equal to 0 to infinity a n z minus a whole to the power n plus n is equal to 0 to infinity bn divided by z minus a whole to the power n. Hence proved. So hope you have understood this. So see you in the next video. So thank you for watching. Stay connected and subscribe the channel, and don't forget to hit the bell icon as well. Okay, see you in the next video.